Okay, so we're in the middle of this re-exploration of linear algebra. We talked about change of basis theorem. We said, wouldn't it be nice if we wanted to understand a linear map if we did so in a coordinate system that gave us the most information? So that's what we were doing. We were starting with something described geometrically, and we said, well, we understand it in a convenient coordinate system, convenient basis. Let's use that to figure out the standard matrix. I sort of want to go backwards today. So if I write down a matrix like, say, (4, 2, -3, -3, and I ask you, what does that linear transformation from the plane to the plane do? You start plotting points, basically. And I'm not sure you ever arrive at a very satisfactory answer doing it that way. So I sort of want to analyze, given a linear map, how do you find the optimal coordinate system, the optimal basis in which to understand it? And for purposes of this discussion, you sort of would like to say to yourself, is there a basis with respect to which the matrix becomes diagonal? Because you understand diagonal matrices, they're easy. First vector gets stretched by whatever the number is in the first slot, second vector gets stretched by whatever number is in the second slot, and then you know what it does to everything. So, is there a basis, script B, and I'm not going to keep the primes going today, we're just going to do standard basis in B, with respect to which the matrix becomes diagonal. In other words, I'm saying A is the standard matrix for some linear map. Can we find a basis script B so that T subscript B is diagonal?
We're only working with square,
so what I said beginning of Wednesday was we're only going to do square stuff for the rest of the semester.
Are they non-singulars?
No, they can be singular.
This one is.
This one is not singular.
We use the columns?
How will that help?
Well, if you set one base to be 4, -3, then it will be 2, -3.
Then what? What is T of the first one? Some horrible thing.
1, 0, 0, 1 times those will give you that matrix.
That's not how you do this. You have to write everything in the coordinate system of the basis. You can't just do standard basis and in the domain and this basis in the range, which is what you're doing. So what would it mean to say this is diagonal? So you would say, let P be the change of basis matrix. And what's the change of basis formula we did on Wednesday?
TV prime, depending on what you're looking at it, P inverse equals, in this case, T. So then the opposite way.
Well, no. So all right. So I'm not going to have B and B prime. I'm just going to have standard and script B. So this is like our B prime on Wednesday.
So it'd be inverse. Wait.
P inverse.
P inverse.
All right. That's the formula. In the new basis, we would have P inverse AP. And the question is, can we find the new basis in such a way that this becomes a diagonal matrix? So for reasons that will become apparent to you in a few minutes, I'm going to call my diagonal matrix lambda. So that's what I want to do. So let's just play with this for a second and see algebraically what this is saying. What's this equation saying? It seems to be saying A times P equals P v times lambda. So think about how we multiply two matrices. This is saying A times the matrix of, let's say the new vectors are v1 to vn. Let's say that's our new basis. So then that means the v's will be the columns of my change of basis matrix. And this is going to be change of basis matrix times diagonal. Now, since the matrix is called lambda, I'll make its diagonal entries little lambdas. So what does this say? This says that if you take any one of the columns here, A times that column equals what?
Vi by times
Vi.
little lambda by.
Well, this makes sense if you stop and think about it. If you think about how I defined the matrix representation of T with respect to the basis B, what we said was that if we had this diagonal matrix for T sub basis B, remember when I don't write things they're all zeros, this is equivalent to saying that T of the first basis vector is lambda 1 of the first vector plus none of the others. T of the second vector is 0 of the first, lambda 2 of the second plus 0 of the rest. That's exactly the statement. Right? So using our definition of how you do the matrix in the basis B in terms of what T does to the basis vectors is equivalent to this equation I wrote down here. Not surprising, I got it out of the change of basis formula. Okay? So what are we looking for?
P.
We're looking for P, but we're looking for vectors that form a basis. So we reframe our question. Can we find a basis consisting of n vectors, of course, in Rn, each of which satisfies an equation like this, with the property that the matrix times the vectors, or the linear map applied to the vectors, is some scalar times the respective vector for each basis vector, for some lambda I for each I going from 1 to n. That's what we want to do. So saying you have a diagonal matrix is saying that you have a basis where each vector is stretched by some factor. The factor could be negative, in which case it's stretched and flipped. It could be 0, in which case the vector dies. So if lambda is 0, so note, if the oops, I haven't told you the word yet. If the lambda is 0, that's saying that you have vi in the what of the matrix? Null space. Right. If the lambda is 0, that means A times the vector is 0 times the vector, which is 0. So vectors that give us the scalar being 0 are vectors that are in the null space. All right, so I need a word because I keep trying to say it.
You can take it out in editing. It's on you.
Definition. We say lambda is an eigenvalue of the matrix or of the linear map if this holds for some vector v. But the vector v is supposed to be part of a basis, so what has to be true about the vector v? Non-zero. If there is some non-zero, so that's hyper important, And when I ask you for definitions on the final, if you don't put the non-zero in there, you're losing points.
Write that one
A times the vector is lambda times the vector, or T of the vector is lambda times the vector. And such a V is called an eigenvector. Bless you. Any German scholars in the room?
down. 9.
Auch nicht. So eigen is the German word that's appearing here, and it means proper or belonging to one. So if you look at some old books, they'll call eigenvalues characteristic values because they're characterizing the linear map. If you know the eigenvalues and the eigenvectors, you know the map.
So will there only ever be n eigenvalues?
Aha! Well, at most, right? So for today, everything we've done in this course has been real, but I'm going to start saying, well, are we going to allow these to be complex numbers as well as real numbers? So in the definition I'm giving here, I'm thinking of mapping Rn to Rn. So the eigenvalues are supposed to be our scalars, when we're doing linear algebra all year, our scalars have been real numbers. So we ordinarily require eigenvalues to be real. But you'll see why we might conveniently want them to be complex numbers. We will also allow, at certain times, to have complex numbers, and that's the notation which I don't think I've taught you yet. Well, no, it came up the other day, actually, complex numbers. But I will then specifically call them complex eigenvalues.
Is the big lambda matrix, is that an eigenmatrix? Or is it just diagonal matrix?
It's diagonal, whose diagonal entries are the eigenvalues. I don't think people normally call it eigenmatrix, but you could. I mean, that would be a reasonable name for it. So the question is, how do we go about finding these critters?
Well, you know that the sum of the a's divided by, like the, if you look at it as like multiplying times the matrix, so you have like
Yeah, but if
the
you,
top row, yeah.
here's a matrix. What are its eigenvalues and eigenvectors? Yes, Patrick?
You could say, since A VI equals lambda I VI, you could say A minus identity of lambda in parentheses VI equals 0.
Okay. So you actually just told me, so note that the eigenvectors corresponding to a given lambda are exactly what Patrick said, are the elements in the null space of A minus lambda times the identity. Right? This is saying AV equals lambda V is equivalent to saying A minus lambda I times V is 0. Now there's there's something slightly wrong with this statement. What's the slightly wrong thing?
The eigenvector could be 0 still.
Right, a vector in the null space could be 0. So the eigenvectors corresponding to lambda are the non-zero. So Patrick has told you now, if you knew the lambdas, then you would remember from chapter 4 how to find null spaces. So trust me, you're going to be remembering over the next 3 weeks, or I guess you'll be done in 3 weeks. The final will have been the day before, 3 weeks from today. So for the next 3 weeks minus epsilon, you will be remembering how to find null spaces. But Patrick still hasn't told us how to find what lambdas I should do this to.
Should we always choose a convenient?
This is all we're doing in 2700.
Ah, you did this in 2700, okay.
Should we just choose like the identity matrix, just kind of like we did with convenient basis before?
No, actually, the clue is right here. If you're going to have a non-zero vector in the null space, what must be true about the matrix?
Singular. So it has to have a. Why
Singular.
don't you choose like A11, A22 for lambda?
Won't work.
It won't work.
No, try it. Just subtract 4 from that, you subtract 4 from the diagonals of that matrix, you get 0, 2, -3, -7. That matrix is non-singular. So precisely those that make A minus lambda I singular. All right, now we proved something earlier this semester. If I give you a square matrix and I ask you singular or non-singular, what's a good test? Determinant. So the determinant should be what?
0.
That should be 0. Singular matrices have determinant 0, non-singular matrices have determinant non-zero. So that's what we ought to do. And in fact, so let's do this for reasons that you will see. I'm not going to use lambda as a variable here. I want my lambda to stand for an actual number that works. So I'm going to say, let's consider the determinant of A minus t times I. T is going to be my variable. So let's do this for this example. So what do? I take determinant, and I subtract t times the identity. So I write down my little matrix, but then I want to subtract t times the identity.
So 4 minus t and then 3 minus t.
So I put minus t on the diagonals. And then I want to solve for when that's 0.
Have you done for A minus t?
Say again? Okay, so what's the determinant?
4 minus t times 3 minus t plus 6.
Okay. Here's a situation where most of the time, but not always, but in this kind of situation, the only way we're going to have any idea what's going on is to expand it out and simplify, right? So what do I get? T squared minus t minus 12 plus 6. And then presumably you guys remember basic 8th grade, 9th grade stuff enough.
Minus 3 plus 2.
I remember quadratic formula.
Don't need the quadratic formula all the time. You do recall that the quadratic formula is completing the square.
Yeah.
So the eigenvalues are 3 and -2. So let's go ahead and find the eigenvectors. So I'm going to give you some notation here, just because it saves writing. E of lambda is the notation for the lambda eigenspace. So that means exactly what we've been talking about, the null space of A minus lambda I. So this is a subspace, because it's a null space. It does contain 0, even though 0 officially is not an eigenvector. So the eigenspace consists of the eigenvectors together with 0, so that you have a subspace. So let's just find E of -2 and E of 3. And if, while you're doing this, you find that the only vector you find in there is 0, what do you conclude?
There's no eigenvectors.
Can that happen?
There are no eigenvalues.
No.
You're wrong. They're complex.
I have my putative
They're
eigenvalues.
not eigenvalues
They're not, as I
by
said.
definition.
That was my second guess.
There must be a non-zero B.
They aren't
In order for it
actually-
to be an eigenvalue, there has to be a non-zero v.
They aren't
Except-
actually
Do you have complex
Yeah,
ones?
what are they?
What would that
What
mean?
do we call fake ones that solve this?
Did you have complex ones?
No, 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 we've
there's
got
a-
these numbers.
There's a problem with me then, right?
Something's wrong, is what you're supposed to say.
It's
Either you got the wrong numbers here, or you screwed up your computation here. But one or the other has to be wrong.
So they have to work.
It has to work.
Ugh.
So if you get to a point where you think you have the eigenvalue, but you can't find an eigenvector for it, you've screwed up. Do not pass go. Go back and redo it.
Theodore Shifrin, J.
So I want the null space of what matrix if I'm doing E of -2?
6, -3,
And what do you notice just looking at this matrix? What do you see is true about its rank? It's got rank 1. It's clear that rows are linearly dependent. That's good. That means you have a null space. And what's more, for 2x2s, you really don't need to go through all our chapter 4 algorithms to find the null space. But you can find the null space of this by sight. No. You want a vector whose dot product with the rows is 0.
-2, 1. Or
See, this is going so well.
-1, 3 is my guess.
-1, 2.
Llama wins.
Back.
So you're still pulling in the complex numbers?
Hang on for the complex numbers. You've got real eigenvalues here. Alright,
But
so you-
-1, 3 dotted with 6, -3 isn't 0.
You don't, it's
rows.
Yeah, okay.
Rows. So we call null space of a matrix is the perp of the row space. So 2x2s you can just do by sight. 3x3 is not so. You're going to have to use the algorithm, so we'll get to that. We'll get back to that. All right? So what about E of 3? Null space of
1, 2, -3, -6.
Again, you look at this and you ask yourself,
So,
is this matrix singular? Does it have rank 1 or 0?
yes.
What's the basis?
-2, 1.
-3.
Might as well give yourself the smallest numbers possible.
-3, 1. Is it?
No.
No.
What is with you?
We're doing the columns. He and I are doing the
Well,
columns.
stop it! As a check, but I won't take the time to do it because I don't trust you. As a check, you should make this your new basis. Put them in as columns. And what should happen when I compute P inverse AP? I should get what matrix?
Diagonal.
With what entries?
With the eigenvalue.
In the correct order.
Yeah.
So I should get
So would 3 be first because you
No,
like that?
negative 2 would be first. because
Which
it's-
one was this?
Yeah,
Or
negative 2.
Yes.
0.
Right, so you should be able to check that computation. I'm not gonna do it, but we'll do our share later.
Is there any kind of importance or significance on order of eigenvalues
No.
and vectors?
No.
Okay.
You can, anytime you have a basis that is nice, you can switch them around. It's still nice, but you reorder what you get for your diagonals.
So you can also have your eigenvector be 1, -3.
Sure.
Okay.
Or you could have, if you wanted to, minus a 1/6. I'm just opting to take, if possible, integers, and the smallest ones I can do that will be reasonable.
So, sorry, I know you said this, but to make sure, you cannot have a completely zero eigenvector.
By
By
definition,
Okay.
it is a non-zero vector.
But one of the coordinates can be.
It's a non-zero vector.
How can you know it is -2, 3 instead of 3, -2? I mean, for example.
Doesn't matter. You could put these in either order, and then you would just switch the entries in the diagonals.
Yeah.
You can reorder the basis any way you want. It's not unique. You can stretch them, you can reorder them, not unique. What is unique, the eigenvalues and the eigenspaces are well defined. You can't have different eigenspaces. You have an eigenspace of all the eigenvectors for the eigenvalue.
So what does P tell, or what does knowing the eigenvalues tell?
Well, so now you know what the linear map does. It takes this subspace spanned by this, and it turns it backwards and stretches it by a factor of 2. It takes the subspace spanned by this and then multiplies it by 3. So you could actually draw a picture of what the linear map is doing by saying, you know, here's my basis. -2, 1. So this line is the 3 eigenspace, and this line is the 2 eigenspace, -2 eigenspace. So I know that every vector here gets multiplied by -2, and every vector here gets multiplied by 3. And so we could draw a picture where we make the plane out of parallelograms built out of these shapes, and we would know that those map to parallelograms along the same axes but stretched.
So when you write it using that as a basis,
If you use these guys as a basis, then the matrix is diagonal, which means V1 goes to a multiple of V1 and V2 goes to a multiple of V2 with those
that's
multiples.
unique to the eigenspace.
That's unique to the matrix. So that's a unique characterization of the matrix. If I tell you what the eigenspaces are and what the eigenvalues for those eigenspaces are, you know the linear
That's
map.
unique to,
Right? And if you take any vector, because V1 and V2 form a basis, you can write your vector as a linear combination of V1 and V2, and it gets sent to the corresponding
if you have a
combination.
single matrix in standard form, is there a single,
What do you mean by single?
if you just have one?
So you have a I don't know what your question is. You have a matrix,
Yeah, is that, never mind,
then there's a unique
okay.
diagonal matrix up to reordering them that characterizes the matrix. Those are the eigenvalues.
If A was a singular, non-zero matrix,
Yeah.
would it just go to a line in R2?
Yes.
And you only have one eigenvector?
No, you still have eigenvectors.
It just,
The null space gives you an eigenvector, and the column space is going to give you an eigenvector. Think about projections. We already did that on Wednesday. The eigenvalues are 1 and 0. The column space gives you the eigenvalue 1, and the null space is the perp of that, gives you the eigenvalue 0.
So if you write a vector in terms of those two basis vectors, you could essentially skip matrix computation.
Well, that's the whole point. I mean, once you're computing in the convenient basis, then you're just working with this matrix. So if you do coordinates in your new convenient basis, you're just multiplying by vectors in the new basis, and you're taking negative 2 times the first component plus 3 times the second. That's the point of working in the new basis. Yeah. All right, so P of t is going to be this determinant. So some of you looked at Webbook and said, what's P of t? So notice this is a polynomial in t. When you expand this determinant, it's always going to be a polynomial in t. Because if you think about how you compute determinants,
I can't get over the voice.
You get to replay that.
so determinant of a minus ti equals P of t is called the characteristic polynomial. Those of you who wish to practice your Math 3200 skills, may prove to me that this polynomial has degree blank if a is n by n.
N. It's N because determinant A minus TI, it doesn't equal determinant A minus determinant TI. I'm specific.
I know. It's in the back.
It is, right?
But yeah, it's n. But what Cameron said was not correct. All right? When you do this and you multiply out, think about any of your favorite definitions, cofactor definition for determinants, whatever, you're going to get a term that has the product of all the diagonals in it. And that will give you a power of n. And in fact, that polynomial is always going to start off with minus 1 to the nth times t to the nth. If n is 2, we saw the leading coefficient was 1. But if I had a third term here, you'd have a third something minus t, and you'd get 3 minuses.
But you're always subtracting.
That makes sense, because it's always minus.
So you're always going to have a minus 1 to the nth as your leading coefficient. You're going to have a bunch of terms here. We're going to do some examples, so you're going to develop some intuition here. But what's always the constant term?
The product of all
Product
the
of
eigenvalues.
the values of that.
It is true it's the product of all the eigenvalues up to a sign. So I'll come back to that. But what is the number that's sitting there? If you have a polynomial, in general, how do you find the constant term?
It's the determinant of the matrix row. Yeah, I was thinking that in my head, so it would only...
Put in t equals 0. Put in t equals 0, you get a determinant of a. But when you take a polynomial and evaluate it at 0, you're getting the constant term. Right?
Right.
And so if a is not, or a is singular,
That would be 0.
then one of our eigenvalues becomes 0.
Right. Now, all right, so to follow up on Daniel's comment, notice that if you factor this as in terms of the roots, then I still have to keep the minus 1 to the nth out here to get, right? Because if I have to t minus blah, t minus blah, t minus blah, I would have a t to the nth. So I still need my minus sign in front. So what's the constant term? Well, we said it's determinant of a, but in terms of the lambdas, what do we have?
It's
Yeah.
negative 1 to the n times the product of all of them. Well, negative n plus 1.
No. How many minus? I have minus lambda 1, minus lambda 2, minus lambda n.
Oh, it's just always positive.
Negative 1,
Oh,
2.
yeah.
So it's always going to be what Daniel said. It's always going to be the product of the roots. The determinant is the product of the eigenvalues. Of course it is, because when you've diagonalized, you get the product of the diagonals when you take the determinant. And those are the eigenvalues. And we talked back in chapter 7 about how the determinant doesn't depend on what basis you're in. We actually talked about that.
Oh, and the determinant of P inverse is the reciprocal of the determinant of P, so.
You even did that on an exam, as I recall.
So that goes away.
So recall that in fact, that the determinant of P inverse AP is the determinant of A. And in fact, the same argument will show you that the characteristic polynomial of P inverse AP is the characteristic polynomial of A. The characteristic polynomial will be the same even if you change basis. The same argument, just write out what the definition is and use the properties. Okay, I want to do more examples. So, you're not going to get that much web work to do this before the test, but the next homework assignment you'll have lots of 3x3s to mess with and even larger shaped ones.
So all this will be on the test.
No, I already conceded that the test went through 9-1. Example. What about this matrix? So what's the characteristic polynomial?
T squared plus 1.
So I have to subtract t from the diagonals. So I got t squared plus 1. No real roots.
Complex.
So no real roots. What are the complex roots?
I, positive negative
Plus or minus I. So that these are called the complex eigenvalues, and it's plus or minus I.
Is that because
No. So why does this thing not have any eigenvectors? What's the geometric interpretation? What does the linear map that multiplies by this matrix do to R2?
Yes, that's it.
Doesn't stretch.
No, like switches.
Those of you who've been doing web work should have thought about this very recently. It's a rotation through what
That
angle?
would be cosines.
Well, when you rotate the plane, I guess for you it's that way. Is there a vector that's just scaled, that's just stretched? No, every vector gets termed.
Only the zero.
So it's not surprising that there's no real eigenvalue because there's no real eigenvector. No non-zero vector stays in the same direction. Those of you who have played with complex numbers, and I will talk about this more at the end of the course, I hope, will recall that if you think about the complex plane, multiplying by I, like if you took the point 3 plus I, and you multiplied it by I, what do you end up with? So if you multiply this by I, you get -1 plus 3I. And it actually did exactly that 90-degree rotation. So multiplying by the complex number is doing exactly what the linear map is doing geometrically. So it's obvious that the complex eigenvalues are in fact plus or minus I because that's what gives you rotation plus or minus 90 degrees. So we'll talk more about that later on, and I hope to have time to talk about how this ties into differential equations a little bit. Okay, so let's try to do a 3x3 example before the weekend. Here we go. On your mark, get set. No. You guys are going to start computing. -2, -2, 4. 0, 2, -2. -2, -1, 3. Find me the characteristic polynomial. what do? Subtract t's from all the diagonals, right?
minus 2 minus
B, in case you didn't remember that minus signs sometimes cause you problems doing determinants, here it's going to, you have to pay real attention to negatives.
Here it doesn't matter if you expand along the first column.
So Daniel is observing that the snappy way to do this, I mean, we have our zigzag patterns of doing it, but Daniel's observing that if we use cofactors using the first column, that 0 is mighty convenient. So I'll get negative 2 minus t times what determinant?
2 minus t minus 2 minus 1 minus
Minus 0 times something, plus
minus 2 for 2 minus t.
and to save me some negatives, I'm going to factor out the negative there. All right, what do I get here?
T minus 2, T minus 3.
Minus 2.
Minus 2. Then I have minus 2 times
4 minus 8 plus 13.
So I think what I would rather do here okay, I don't see anything obvious to do here yet. I mean, we could pull out a 4, but what happens here? So t squared
minus 5t plus 4
plus 6 minus 2,
plus 4.
and then I get plus, I'm going to factor out a 4, I guess. So I'll have 8.
The 8 will cancel.
That'd be
So how
negative,
many, what have I got here?
negative 1 minus t.
Yeah, maybe I shouldn't have.
Plus.
Negative 1,
Minus t.
so I shouldn't have factored that. Okay, so you're saying t plus 1 here? Let's see if that's right. Do I have negative 8t? I have negative 8t, and then I've got 4 minus 8 is negative 4 times negative 2 is plus 8. Wait, why did you say?
It's t minus 1.
Yeah.
My bad.
That gives the output.
Okay. Be careful with negatives, because small mistakes are going to cause you all sorts of problems. At this point, please only multiply all this out as a last resort. What can you do with this?
T minus 1, T minus 4.
And looky here. So don't just expand everything out and then hope you're going to be able to factor back. I'm going to talk to you about how to do that. So I'm going to talk to you about the algebra tricks. But you have a t minus 1 we can factor out.
Could do negative.
In fact, I can factor out a negative t minus 1, as Jonathan was just going to say. So what do I have here? I have t plus 2 times t minus 4 plus 8. Now let's simplify.
Please drop the negative, because we're equaling to 0.
I'm still trying to write things that are correct. So the characteristic polynomial will have the negative in it, even though we run it factored out. But, all right, what do I have here? T squared
Minus 2t.
That's it.
minus 8 plus 8. So what have I got? Minus t factors out t minus 1, t minus 2. Look at that. So what are the eigenvalues? 0, 1, and 2. Once again, we have a 3 by 3 matrix. We have 3 eigenvalues. But, you know, obviously you could have repeated roots showing up here, and we're going to talk on Monday about what happens when that happens.
Do you have the 0 in the diagonal, wouldn't that make one of the eigenvectors 0?
No.
You minus 2.
Oh, yeah.
So what are the eigen, I don't want to do all three of these, but let's do one eigenspace just for practice.
E is 0.
E of 0, all right. So I want the null space of E of 0. So I want the null space, I want the
It's just that.
You're just a null space.
null space of A. So this is going to be the null space of A. So I'm going to take A and try to remember how to do null space. What should I do first?
We're going to reduce directional form.
I want to go to reduced echelon form, but what should I do first with all these 2's?
Divide out a negative 2.
So get rid of the negative 2.
You do it for the second row as well.
Do it for the second row as well. And then I want to use my first pivot to kill off this negative 2. So what's the last row going to become?
0, 1,
And then negative 1.
negative.
1, negative 1.
Negative 1. Aw, isn't that cute? So we can actually kill the bottom row with no big deal. I have the second row, and now what do?
1,
Subtract the
0.
Subtract the second from the first, right, to kill the column.
It's
1,
1,
0,
0, negative 1.
Is it 1, 0, negative 1? Does everybody agree? So what's a basis for the null space? What's the eigenvector corresponding to lambda 0?
1, 0, negative 1, 0, 1, negative
No,
1.
no, no,
1, 0.
no, no.
1, 0, 1, 0.
No.
1, 1, 1.
1, 1, 1. Remember?
Less than it.
This is the free variable, and you solve for the pivot variables in terms of the free variable. As I said, you'll be reviewing, and you similarly can do the other two.
If we don't get rid of all zeros, we already did something wrong, right? Because it has to be not singular. Or it has to be singular.
Has to be singular. So if you cannot find an eigenvector, then either you've messed up the arithmetic here, or God forbid, you actually messed up back here and that wasn't really an eigenvector.
And then you start over again.
Well, but first, make sure that
Yeah.
you didn't make the mistake here.
Let's go back all the way back. It turns out just
All right, so Ken's asking the question I'm
Sounds
going to
like what I do in web work.
Ken's asking the question I'm going to focus on Monday. If you have 3 eigenvalues for a 3x3 matrix, what do we expect? Well, we're going to get 3 linearly independent eigenvectors. But suppose we had 1, 1, and 2. Suppose you have repeated roots, then what happens? And that's exactly what we're going to explore on Monday. Now, I want to just make a comment here in my last couple minutes. We were lucky here, right? This was lucky. Suppose that I'd gotten some polynomial that didn't have 0 as a constant term, and I didn't see any obvious factoring for it. What would I do?
Cry.
You could cry. So
Nice form of alpha.
you won't need this for this week's web work, but you'll need it for next week. So I want to just point out there's something that you should know from high school math, but you don't. But Haley knows it from Math 4000. And you all will learn that next year, those of you who take it.
Yeah.
It's called the rational roots test.
We did that in high school.
Aha, you see, you do know it from high school.
No.
It's still in
high school.
Oh, that's why he knows it. So if you have a polynomial with integer coefficients,
The possible roots,
all right, hang on a minute. Hang on a minute. So if all the coefficients are integers, I've forgotten whether we've used that notation before.
Yeah.
Then any rational root, I can't help you with irrational numbers, but any rational root that this polynomial has must be of the form P over Q, where P divides the constant term, so it's a factor of the constant term, plus or minus, and Q divides the leading term, a sub n. So you have a hopefully small finite list of roots to try. You hope you find one, and then what you do next is you say, if I have a root, I can then divide by t minus the root, and I'll get a lower degree polynomial. And you're not going to have to do this for 5 by 5s. So if you have a 3 by 3 and you do this, you get down to a quadratic, and then you're back in your comfort zone. Okay. So we'll pick up with this on Monday.